Now let us move on to another topic which is to try and identify the effective impedance of a PN junction. Okay, so just summarize the current voltage characteristics. We found that in a PN junction you had a depletion region, we derived electrostatics for it, and we found that when you apply a forward bias we had excess holes being injected in the N type and excess electrons being injected into the P type, and those excess holes would recombine and therefore you had a concentration gradient, and similar likewise with the N injected electrons. And this concentration gradient gave rise to a diffusion current for holes and a diffusion current for electrons, and we computed the diffusion current at this boundary at equal to minus xdp and at x equal to xdn, and therefore we identified the complete current voltage characteristics for a PN junction diode. So that is what we did. So now we know the current voltage characteristics, and we found that J was some constant into e to the power QVA by KT minus 1, and just to recollect what this constant was, it had all these terms in it. Okay, it had Q, dN, ln, npo, dp, lp and pno. Okay. Lp is the diffusion length, dp is the diffusion coefficients. So this is the current voltage characteristics. Now however, there are some finer points to all these discussions, okay, and we will sort of discuss these finer points by looking at the calculation of the impedance of a PN junction. Okay, so if we have a PN junction in a circuit, what is the effective representation for this device? So this very strongly depends on whether you are operating in reverse bias or in forward bias. Okay. So in reverse bias, okay, so if you recollect your metal semiconductor junctions, we had a depletion capacitance, and this PN junction is also going to offer an effective resistance. Okay. So what we are interested in is something called the small signal impedance, and we have discussed this before, and what it implies is that if you have this device in a black box, so let us say here you have your PN junction diode in a black box, and you have these two terminals, and you apply maybe so you apply a DC bias voltage firstly, and on top of that bias voltage you apply a small signal AC. Okay, so you have a DC voltage, and on top of that you have a small signal AC voltage, and around the small signal behavior you can linearize this device, and therefore the small signal impedance that we are looking for is basically your response of the device to this small signal, which is how does the current through the device vary in correspondence with the applied small signal voltage. So this is the small signal impedance which we are interested in. So if you think about the PN junction in reverse bias, so if this is the band bending diagram, you have a junction here and you have your depletion region boundaries here. So that is the P side, that is the N side. So let us say this is the equilibrium condition. So in reverse bias the depletion region increases a little, right, and the band bending becomes a little steeper. So if I were to fluctuate, if I were to keep my device in reverse bias, so which means that I apply a large negative voltage, so VA is less than 0, and on top of that I apply a small signal AC voltage. What is the effective small signal impedance of this PN junction? So that is the question asked on this slide. Okay, and the answer is there are two components here. You have a heavily doped N side and you have heavily doped P side, and at the interface you have a depleted region. Okay, so you have your P, you have your N, and this depleted region has got no free carriers, but these two regions are almost metallic, right. You have a large number of electrons, you have a large number of holes, and this region is almost metallic, but here in the middle you have a depleted region. So when I say almost metallic, it is not to be taken in the sense of it being treated as a metal. What I mean is the resistance is very low. So you have a device that looks like a capacitor, okay, and we have already looked at this in the metal semiconductor junction, wherein you have these two regions and then you have this depleted region, and because of the small signal fluctuation the depletion region widths fluctuate. Okay. So if the voltage goes more negative, then so let us say we are this is our reverse bias. So let us say we have applied say minus 5 volts, and let us say we have a small signal AC here. So if the voltage is in this region, it is low, it is more reverse bias than 5 volts, and therefore the depletion region increases and uncovers more fixed ions, and then as it goes to 5 volts it reaches its mean depletion width, and as it goes to above, slightly above 5 volts, then it covers some of the ions and it reduces in size, and it performs a little fluctuation, and it is this fluctuation that results in an effective fluctuation in the charge. And since there is an effective fluctuation in the charge, we can calculate dq by dVA and say that this is your effective small signal capacitance. So that is what we did in the case of a metal semiconductor junction. So what is dq by dVA? Q is nothing but Nd into xdn on the N side and Na into xdp on the P side. Since xdn and xdp are changing with respect to the bias, okay, you have your dxdn by dVA plus dxdp by dVA giving you this capacitive component. Now that is one method to calculate the capacitance. The other method to calculate the capacitance is to simply think of it as a parallel plate capacitor in a very crude manner, okay, because these two regions have got low resistance and this region here is depleted, and therefore if the junction has got an effective cross section area of A, my capacitance is simply epsilon A by xd, which is xdn plus xdp. And since xdn and xdp are dependent on the built in potential and the applied voltage in this manner, this is my total small signal capacitance. Okay, and we saw the similar argument even in the case of a capacitance of a Schottky junction, a metal semiconductor Schottky junction. So that is the small signal capacitance of a diode in reverse bias. Okay, in forward bias there is something more interesting that happens, we will come to that. What about the resistance of a diode in reverse bias? We already know the current voltage characteristics, and therefore my small signal resistance is dVA by dI, and that is easily obtained by taking the derivative of dI by dVA and then taking the inverse of that, and you will find that the small signal resistance is kT by Q into I plus I naught, where what is I naught? I naught is nothing but your J naught times the cross section area, and I is nothing but the current density into the cross section area. Okay, and we have already seen what J naught is, all the parameters it depends upon. So in reverse bias, this is the small signal capacitance and that is the small signal resistance. Okay, but in forward bias, okay, let's sorry, that's a repeat of the slide. In forward bias, you do have a same capacitive component. Okay, that capacitance which we discussed is something called as a depletion capacitance. You do have a depletion capacitance. You once again do have a small signal resistance, but you have an additional capacitance term which is called as the diffusion capacitance, and I will tell you what this is. And another parameter that now starts playing an important role because the currents are now larger is simply the series resistance due to the PNN junctions. This was there even in the case of a reverse bias, but for practical purposes it need not be considered because the currents were not very large. But if the currents grow very large, then this series resistance can cause a huge significant voltage drop across the PN junction, and that series resistance is simply because of the doping of your N and P type, and due to any metal contacts that you may have or any external circuit, this adds in a series resistance. Okay, but apart from that, you have your depletion capacitance, you have your small signal resistance due to the diode behavior, and you also have something called as a diffusion capacitance. Now we have already looked at depletion capacitance, we will not worry about that. We have already calculated what dVA by di is, which is your diode resistance, we will not worry about that. The series resistance is quite simple to calculate because the resistivity is simply Q 1 by Q into mu n on the n side, and in the case of p side is 1 by Q mu p on the p side. Okay. Mu n into n, where n is the electron concentration and mu p into p, where p is the hole concentration. Okay, so that is your series resistance if you only consider the diode alone. But what we have never discussed so far is this component called as diffusion capacitance. So what is the diffusion capacitance? Very intuitively. Okay, now in forward bias, what we have done is we have injected the minority carriers, right. So we now have a minority carrier injection because the large amount of carriers diffusing across the junction. So if we have to apply, if we were to change, and we already noticed that this term was P n naught into e to the power q Va by kT minus 1, and this function, that was also my component which was B, and this function was given by B to the power minus x dash by Lp. Okay, just to recollect. So obviously this minority carrier concentration depends upon Va, and the concentration at every point in space after that depends upon Va. Okay. So if you take a very broad definition of what capacitance means, it is if I were to put this diode in a black box. Okay, so if I were to put this diode in a black box and I vary the voltage across, and the amount of charge, so as the voltage varies, the voltage small signal fluctuates, the total charge content inside this black box fluctuates. Okay, and it is this ratio dq by dVA which is my capacitance, that is my small signal capacitance. In reverse bias there was no minority carriers being injected. I mean it is not considered at all, okay, because the current is purely drift based and we really never worried about the injected minority carriers. And therefore the only capacitance we considered in reverse bias was the depletion capacitance. We never bothered about this new component here, the diffusion capacitance, and therefore this dq was only due to the movement of xdn and xdp. So any voltage I apply, the way the black box would respond is by uncovering or covering the fixed ions it would uncover or cover the fixed ions, and that was the only response the device gave, and therefore we could model it as a parallel plate capacitor and get away with everything. But now we have a rather tricky component here, okay. But in forward bias, not only do we have the depletion capacitance due to the depletion width change, which is already accounted for, but this minority carrier concentration will also change. So if I were to apply my small signal, if the small signal, so now we are in forward bias, let us say we have got a forward bias, let us say it is plus 1 volt, and on top of that I have a small signal fluctuation. So as the small signal goes above 1 volt, this minority carrier concentration will increase, and as it goes below 1 volt it will decrease, okay. So therefore any fluctuation here will be seen like a wave like response in the minority carrier concentration, the injected minority carriers. So as this applied voltage fluctuates, not only would the depletion width fluctuate, but also the injected minority carrier concentration will also fluctuate, and this fluctuation in charge was never accounted for in the calculation of the depletion capacitance, and that fluctuation in charge is accounted for in what we call as a diffusion capacitance, okay. So now that is a very qualitative understanding of what diffusion capacitance is, but how do we quantify this, okay. We want to write a nice mathematical expression for the diffusion capacitance, and what we will do is we will quickly look at how to go about calculating the diffusion capacitance. So clearly it arises from the concentration variation, the transients of the injected minority carriers, right. So that is what is causing the diffusion capacitance. So therefore our starting point must be, in order to derive the diffusion capacitance, our starting point must be the continuity equation, but not in steady state. We must take into account the transient, okay. So we are no longer interested, if it was steady state we could simply say that this component was equal to your d delta Pn by delta Pn by tau p and just get away with it. But now we want to look at the transient response, okay. So transient response of the injected carriers, and therefore we have a time dependent derivative term on the left side. It is not steady state, and therefore if you recollect your continuity equation, you will find that this becomes your continuity equation, okay. Now this is the total injected, this is the difference between the total injected charge and the equilibrium charge. So that is my delta Pn. Now because of the DC bias, it has got a DC component, and because of the applied AC signal it has got an AC component also. So this is the component that we are interested in, it is fluctuating. The DC component has already been accounted for calculating the DC current, okay. So we looked at this already. So in general this delta Pn, the injected carriers, has got a DC part and it has got an AC part, and I will define this AC part with this little tilde at the top, okay, and the DC part with just an over bar or just a straight line there, okay. So this wavy line on top of delta Pn describes the AC part. So now I can split this continuity equation for the DC and AC part. So if the DC part, this time dependence is all 0 and we are talking about steady state, and therefore this is my continuity equation that we have already looked at and solved. That is what we used for the current, there was no fluctuating voltage component there. But now since we have a fluctuating voltage, the AC part alone, that is if we get rid of the DC component of it and we take only the AC component, we find that this is the continuity equation of interest. There is a transient, there is a diffusive term, and there is this recombination term, okay. So now how do we solve this continuity equation? It has got a time and it's got a time and space dependence. Okay, so usually what we do, that's the best approach for such things, is to use a separation of these two variables. Okay, so we will say that if these two are truly independent, okay, and it so happens that it's a good enough assumption and we can get away with it. Okay, we can truly separate the time and spatial component and get away with it, and therefore we will do that, and I will tell you why very intuitively. Okay, so this is the AC component of the injected charge, and we will say that that is equal to delta Pn star, okay, which is the magnitude, which got only the spatial part of it, into e to the power j omega t, which has got the time dependence. Okay, so very intuitively you can think of it as a wave, right? It's you're fluctuating. It's like somebody holding a string which is tied to one end, and it's tied to one end implies it's like if you take the long base approximation at x equal to infinite, at x dash equal to infinite, you have that end tied to delta Pn equal to 0, that is not moving. Okay. And then on the other side they are fluctuating the voltage. In other hand, somebody is pulling string up and down, or you can think of it as water, okay, either way, and you have this little variation of delta Pn in space and in time, and it's got this wave like behavior, and therefore very intuitively we will just say that this time dependence is simply e to the power j omega t. Okay. We are getting away without explaining a lot of things, but we are using strong intuition here, and we are actually fine with these approximations. So now we will just substitute this expression for delta Pn, the AC component of delta Pn is given by this, and we will substitute this approximation inside our continuity equation. And when you make the substitution, you see that this time derivative becomes j omega delta Pn e to the power j omega t. This term here will give you this component, that's delta Pn star there, okay, and this component is simply a direct substitution here, and you find that all the e to the power j omega t terms conveniently cancel away, and you will end up with this expression, okay, which is neatly written out over here. Okay, so that's what the continuity equation boils down to if you were to take only the AC component and use a separation of variables. Now if you look at this term, okay, inside the bracket, inside the square bracket, it is a complex number. It is 1 plus j omega tau p by dp tau p. Now it is a complex number, but just think about it a little. Omega tau p is a dimensionless term, okay, and 1 plus j omega tau p is some complex number that has got no dimensions. Okay, so we will just say it is some complex number. Okay. dp tau p is nothing but your LP square. Okay. So what you have here is delta Pn star by LP square into a into this complex number 1 plus j omega tau p. Now we will take these two terms, the complex number divided by LP square, and we will say that, okay, we will say that this entire thing is equivalent to 1 by LP star square, where LP star is some kind of a complex diffusion length. Okay, so just a mathematical construct here. It is a complex diffusion length. It is LP square divided by 1 plus j omega tau p. Okay, so that's our mathematical construct, and we are doing it in order to get a differential equation that's very familiar, which is d square delta Pn by dx square is equal to delta Pn by LP star square. So delta Pn star by LP star square. LP star is a complex number. Okay, it is in fact the square root of this complex number, if you wish. square root of this particular term. So, now we already know the solution to that equation, let me just rewrite that equation here. So, you have your d square delta Pn by dx square is equal to your delta Pn star by Lp star the whole square. Now, it has just come to my attention that I have missed out mentioning something here. Okay. So, throughout I have been using this variable x. Okay. So, please do remember this x corresponds to x dash. Okay. We are still interested in the translated coordinate system. Okay. So, if you have any queries, I am sure all of you understand this by now, but if you have any questions you can just get back to me on that. So, so we are talking about x dash. Okay. So, if you still use our old PN junction diode diagrams, but nevertheless I think you understand the context of what we are talking about. And the solution to this differential equation is again given by this particular term here, where B is your injected carrier minority carrier hole concentration at the depletion boundary on the n side, and that is equal to Pno e to the power. In the previous case we saw it is QVA by KT, but now it is going to be QVA plus the small signal VA by KT. The small signal VA has got a time based component. Okay. So, B turns out to be this particular term. It is going to be Pno e to the power Q into the DC voltage plus small signal voltage by KT minus 1. Okay, so that's the expression. So, there is a minus 1 term here which is missing. Okay, and we could now approximate this. Okay, we can approximate this and say that this particular term is nothing but Pno e to the power, we will just take out the large signal or the DC components out KT, okay, and you leave behind only the small signal part, but we will approximate that small signal part, okay, and we will say that it is, we will use a Taylor expansion on that and say that it is 1 by QVA by KT minus 1. Okay, so there is a minus 1. Sorry about all these typos. And therefore, the small signal component, the small signal part alone becomes just this. Okay, so all this cancels away and this is your small signal component. So, what we have done here is we have gotten rid of the exponential with regards to the small signal component. We are just trying to linearize this and say it is dependent on VA. Okay, so that is the whole point of small signal analysis, which is the ability to use a Taylor expansion and linearize things, and we have done that here. And therefore, delta Pn at x equal to 0, okay, is going to be B e to the power minus x by Lp star, and at x equal to 0 it is simply equal to B, and therefore, delta Pn at x equal to 0, delta Pn star at x equal to 0 is simply given by this expression, wherein we have used Taylor expansion and linearized the VA term. Okay, so, in summary, this is quite important. This is the expression that we will use. And now, what is the current component? The current is because of the diffusion term, right. It is Q into A, area of cross section, into dP into d delta Pn star by dx, and that turns out to be this, because we now know what is B, and we now know what is B into e to the power minus x by Lp star, and therefore, we know what this derivative is, and we can now find the current at x dash equal to 0, and you will end up with this expression here. So, that is the current, that is the small signal current due to the fluctuation, due to the voltage fluctuation, the small signal voltage fluctuation set at a DC bias of capital VA. And therefore, the impedance term, a general complex impedance, is dVA by dI, because of the I being that small signal current, and that will end up being a number like this. Okay. And since it has got this term LP star, this is definitely a complex number, therefore, it has got a real term and a complex term, and the imaginary part of that is the diffusion coefficient. So, it is quite understandable if the last bit was quite confusing, but it is just a mathematical follow up of everything that we have done. So, once again, if there is any questions on this, feel free to send in a message. Okay, but that's a very intuitive analysis of what the way to go about calculating the diffusion capacitance. Okay, it is because the key message here is it's because of the fluctuations in the injected minority carriers, which is quite significant in forward bias, and therefore, the diffusion capacitance is quite important when you are talking about a PN junction in forward bias. So, therefore, to summarize, the PN junction in forward bias has got different terms. It has got its own small signal resistance, okay, that is dou VA by dou I. It has got its depletion capacitance, which is say epsilon as A by XD, and then it has got its diffusion capacitance, which is defined by this analysis here, and it has got a series resistance, which is important because of the large currents and therefore more significant voltage drops. It is not advisable to ignore the series resistance, because the doping profile is not defined, the metal semiconductor junction is not defined, etc., etc. So, this is the equivalent circuit of the PN junction in forward bias. So, to summarize everything we have done so far, we looked at what the PN junction is, we looked at the electrostatics, we looked at the current voltage characteristics, and the key message was that the current voltage characteristics has got a rectifying nature to it, and it is because the diffusion of minority carriers that you have a current voltage characteristics defined by an exponential function. And then finally, we used all this information to calculate the impedance of the PN junction diode in forward and reverse bias.